Today we're going to learn how to calculate an empirical and molecular formula. Now, what is an empirical formula? An empirical formula is the simplest ratio of atoms that can combine. Molecular formulas are what you've been writing. When we do the nomenclature and you ask to write a correct formula, that's a molecular formula. An empirical formula is the simplest ratio of those atoms. And let me give you an example. We have a molecule called ethane. Ethane is C2H6. It's 2 carbon atoms and 6 hydrogen atoms. That's the molecular formula for ethane. However, we can simplify the subscripts. And so the empirical formula for ethane we would write as CH3. It essentially gives us the simplest ratio of atoms to one another. It's like simplifying a fraction. If you have a fraction of 8/12, you can simplify that to 2/3. And that's what empirical formulas are. And the reason we calculate empirical formulas is so we can identify what an unknown substance could be. Because when you run an analysis of it, you're going to get the simplest formulas for those. And then once we have an empirical formula, we can calculate a molecular formula, what it is. So let's look at this first question here on worksheet 6. It says empirical and molecular formulas. And the question tells us that we have a compound and we know it's 82.7% carbon and 17.3% hydrogen. We're also given its molar mass at 58 grams, and so we want to know what the empirical formula and the molecular formulas are for this compound. So here's a question that gives us information, the percentages of each element, and perhaps we did a percent composition lab just like you did or will do in the lab. And we found out that there's these percentages of carbon and hydrogen. So our first step is something we tell you never to do in science, and that is we're going to allow you to assume something. We're going to allow you to assume that we have 100 grams of this substance. And so if we assume we have 100 grams and 82% of it, or 82.7% is carbon, then we can assume we have 82.7 grams of carbon. And if we have 100 grams and 17.3% of it is hydrogen, we can assume we have 17.3 grams of hydrogen. That makes a nice little conversion. If you're already given grams, you can just leave it in grams, obviously, but a lot of times if you do this in the lab, you're going to find percentages. So our first step is just convert it to grams. Second step now, we want to figure out the number of moles. And that's something that you've done many times. So we want to figure out the number of moles of carbon. So to do that, we just do a simple conversion of grams to moles. There's 12.01 grams of carbon in a mole. Just get that number off the periodic table. And for hydrogen, we have 1.01 grams of hydrogen per mole. So we're going to these out on our calculator here. We'll take 82.7 divided by 12.01. We get 6.8859. We're going to round that to 6.89 moles of carbon. And then for hydrogen, 17.3 divided by 1.01. That's going to give us 17.128 or 17.1 moles of hydrogen. Okay. So we're going to convert this to moles. Now, we're going to look and see which one's the smallest number. Obviously, 6.89 is the smallest number of moles. So we're going to divide now by that smallest number. We're going to divide this one by 6.89. I know it seems redundant, and obviously that's going to equal 1. We're going to divide 17.1 divided by 6.89. So if we do that, if we take 17.1 and divide it by 6.89, we're going to get 2.48 or 2.5. That rounds very close to 2.5. When you do this calculation, you're either going to get whole numbers or you're going to get numbers to 0.5. These numbers here are your subscripts for your empirical formula. So our subscript for carbon is 1, and our subscript for hydrogen is 2.5. I'm just going to write in this one so you can see it. Now obviously you cannot have a 0.5 for a subscript. You cannot have half an atom. So in this situation, if you get a number that is a 0.5, like this 2.5, we need to multiply them both through by 2. So if we multiply 1 times 2, obviously we get 2, and 2.5 times 2 will be 5. So our empirical formula is going to be C2H5. Like I said, most of the time when you do this division step, you will get whole numbers here, and those whole numbers become your subscripts. However, if you do get a 0.5, 1.5, 2.5, 3.5, then you need to multiply both of them by 2 in order to make them whole numbers, because they have to be whole numbers. So this right here is your empirical formula, C2H5, your simplest whole number ratio. Now the molecular formula is found by taking the given molar mass. So I'm given the molar mass of the molecular formula is 58.0 grams, and you will always be given that number because you have to be. And we're going to divide that by the molar mass of C2H5, the molar mass of your empirical formula. So the molar mass of C2H5 is 12.01 times 2. That's our carbon. 24.02 plus 5 hydrogens. 5 times 1.01 is the molar mass for hydrogen. Just getting those numbers off the periodic table. So the molar mass of this substance is 29, essentially 29.0 grams per mole. Okay, I'm going to take that number and we're going to put it right here in the denominator. We're going to divide it into 58. So 58 divided by 29 is 2. You will always get a whole number for this measurement. You will always get a 1, 2, 3, or 4, maybe a 5. But it'll always be a small whole number. And what we're going to do with this number is we're going to multiply it by the subscripts on the empirical formula. So our molecular formula is going to be C4H10. This is how the molecule exists. 4 carbons and 10 hydrogens. This is butane. Its empirical formula, its simplest ratio between the subscripts is C2H5. So let's just go through these steps again. These are all simple math steps, but it takes practice to put them into the right order. So the first step we did was convert grams to moles for all of our elements, both carbon and hydrogen. Then once we determined the number of moles, we determined which one's smaller and divided by it in each step. So this divided by itself was 1. This into the 17 moles of hydrogen was 2.5. These numbers become our subscripts for our empirical formula. However, because we have a 0.5, we just had to multiply those through by 2 to get our C2H5, our simplest subscripts. Then in order to find the molecular formula, we took the given molar mass, which was 58, and divided it by the molar mass of the empirical formula. That resulting quotient, then we took and we multiplied by the subscripts to get our molecular formula. The math is simple, but the steps do take some practice.